Bismillahirrahmanirrahim. I'm Muhammad Rizwan from BS Biotechnology, and my resource person is Dr. Hammad Majeed. Today I'm presenting here the topic is microfluidics. First of all, we discuss the introduction to microfluidics. A microfluidic can be a state device demonstrating the high density of microfluidic channel that can be contained with very small size. The emergence of microfluidics in the recent decades has provided unprecedented, precious, and continuous flow technology, bringing new capability to a wide range of fields from biological analysis and chemical synthesis to optics and information technology. Microfluidics device made from polymer glass, silicons, metals, and other materials manipulate small volume of fluids through geometrically controlled environments, often separated into distant subunits such as reactors, mixer, and detectors. Microfluidics owes its distinct advantages in this field to some fundamental characteristics. It is characterized by linear flow or those with low Reynolds number, indicated the relative importance of internal forces to various forces in a fluid, which help eliminate any backmixing in the system that may be caused by fluid turbulence, such as show a schematical illustrating the diffusion based mixing that linear flows in microfluidic device facilitates. And the next is some advantages of microfluidics in chemistry. The first advantages of microfluidics in chemistry: small reagent volume, microreactors, and footprint. The small size of microreactor provides the very practical advantages of having a smaller footprint than conventional flow reactors and smaller yet than microscales reactor due to in part to the smaller heat exchange equipment needed from the more efficient microfluid heat transfers. And the second advantages of microfluidics: selectivity of microreactors. As is often the case with chemical and biological reactions, multiply products can be generated from a given set of reagents depending on the local condition of the reaction. With the control over these conditions, gradient by microfluidics such as temperature and residence times, individual compounds among multiplied that could be produced by a given reaction can thus be selectively produced with high degree of precision. And the third advantages of microfluidics: rapid safe reaction in microreactors. Microreactor can more easily be optimized and closely monitored to not run for any longer than is necessary to reach the reaction endpoint and are accordingly reported to have greater space-time yields. Thus, even if the rate limiting reaction is unchanged, microfluidic reactor will allow for more efficient and consequently more rapid chemical processing. Furthermore, chemical reaction in microfluidics device can be performed with more inherent safety than before and with the ability to handle high pressures and temperature at small scales. Only small volume of reagents are used in microreactors. Additionally, exothermic reaction can be more safely performed due to high surface area to volume ratio and rapid heat transfer that until. The next is scale out potential of microreactors. In contrast to the scaling up of microreactors, increasing their characteristics dimensions for increased productions, the true strength of microfluidic come in scaling outs. These systems, instead of increasing the size of microreactor, scaling out simply denotes the increases of the number of microreactors in order to produce a parallel networks. Green chemistry with microreactors. Here the characteristics high surface area to volume ratios exhibited in microfluidics again proves to be beneficial in reducing the amount of energy required to efficiently meet thermal requirement of the reactions. The increased selectivity of microfluidic reactions can allow from the exclusions of undesirable reactions products as well as more the active recycling of useful reagent with the less filtering resulting in minimal reagents consumptions and minimal cleanups extras. And the next is disadvantages of microfluidics in chemistry. The first point is microfluidic as an enabling or replacing. While it is unadopted, the microfluidics technology can enable a wide range of chemical processing. It primarily barrier in its more universal implementations lie primarily in just that it is viewed as an undeniably technology paraphrase more than the replacing technology. Much of the development of microfluidic techniques in chemistry stem from applications that are considerable, difficult or hazardous at larger scales, where the use of microreactors can bypass certain limitations that exist in conventional process conditions. The next point is multi-phase reactions with microfluidics. Multi-phase reactions have long presented channels for microfluidics. The high surface area to volume ratio inherent to microfluidic reaction present great potential advantages for multi-phase reaction, but complications with the clogging of solid reagents in particular has been a concern. The next is microfluidic cheap material. The choice of microfluidic materials dominate its functions while this present a variety of options to the operators factors such as cost, complexity of fabrications and suitability for involved reagent presents dissents, pros and cons for each type of materials. And the next is microfluidics in chemistry applications. Due to the numerous benefits of microfluidics discussed above, many stemming from the scale depending process of heat and mass transfer, microreactors have found application in a variety of academic and industrial areas, such as synthesis of non-materials, natural products, and various small molecule drugs and pharmaceuticals extras. The first one is hazardous reaction with microreactors. The relatively small length scales and amount of chemical materials involved with the microfluidics significantly mitigates the risks surrounding hazardous materials and exothermic reactions. Reactions with these hazardous characteristics are difficult to scale to any industrial level with the conventional bench reactors. And the next is Commercialize of Microfluidics, the containing growth in commercially available, available microfluidic device has helped bridge the gap between academic research and industrial application in relevant fields. The commercial availability of microfluidic devices allow research to assess this powerful technology without the technical skills and experience needed to fabricate the device themselves. Furthermore, any chemical process developed with microfluidics in academic setting with can be easily be scaled up. Reaction optimized with microreactors. Due to their rapid response time to programmed change in the microfluidic environment, microreactors are ideal for performing reaction optimizations. A reaction optimizations can, for example, consist of mapping the reaction phasing space by varying reaction factors such as temperature, reagents, concentrations, and residence time, then rapid sampling product formation in near to real time in order to determine reactions optimum condition. Droplet based microfluidics. The more recent development of droplet based microfluidic has significant influenced chemical synthesis, micro and nano fabrications, and synthesize biological. This alternative method of microfluidic process involves splitting fluid stream into small discrete droplet and provide the added benefit of removing the effects of tires dispersions and the subsequent increase as of droplet transports. Reaction performed in droplets have been shown to have significantly affected reactions kinetic, showing increased equilibrium and forward rate constant as the droplet radius. Droplet based technique by isolating reaction from the microfluidic channel walls can also prevent microfluidic channel flowing, a problem that can sometimes occur in continuous flow methods. Thank you for listening.